As the world works toward a global clean energy transition, collaborations that bring people together across disciplines, sectors, cultures, geographies, and generations, and that arm them with the most advanced tools and technologies are essential. Further, the social dimensions of this needed energy transition are starkly exposed by the urbanization of the world's population. Almost all of the population growth expected worldwide over the next 3 decades will take place in cities. By 2050, the world's cities will need to grow to accommodate 2.5 billion additional people. Our built environment currently is responsible for nearly 40% of annual global carbon emissions in building materials and construction, and in building operations, especially heating and cooling. So as we expand our cities, we also must move with great urgency towards energy efficiency. Those countries that already are highly urbanized must retrofit their aging urban infrastructure for net zero emissions and climate resilience. Those countries that today are less urbanized will experience the fastest growth in their urban populations and face different challenges. The stakes are high. While urbanization traditionally has been a force for prosperity, as cities concentrate both economic and educational opportunities, without the right policies and infrastructure, we may add to the 900 million people worldwide who currently live in overcrowded conditions, in unsound housing, without access to clean water and sanitation. While economies of scale mean that cities can use natural resources highly efficiently, without rational planning, growing urbanization can lead to sprawl, pollution, and environmental devastation. Today, our cities are not optimized, either for energy use or for the health and well-being of all their citizens. Our built environment does not interact intelligently with the electrical grid, where there is one, with transportation infrastructure, or with supply chains. New approaches and new technologies offer the possibility of seamlessness. The opportunity here is to view each city as a system of systems and to allow sophisticated interactions and exchanges of information among them in order to achieve a collective multi-scale intelligence to the benefit of all. Decarbonizing the many systems of our daily lives and strengthening their resilience requires an integrated approach. Universities are ideal platforms for this work. That is why Rensselaer Polytechnic Institute is launching and leading the Institute for Energy, the Built Environment, and Smart Systems, or EBIS, with distinguished partners that include industry leaders Siemens and Lutron Electronics, the building engineering consulting firm Thornton Tomasetti, the international architecture firms HKS, OBMI, and Perkins and Will, and the Brooklyn Law School in New York City. EBIS will focus on deep decarbonization and climate resilience, bringing together architects, engineers, and policymakers to devise responsive new materials and building platforms for net zero structures, and to model and design cities with integrated emissions-free transportation, communications, and supply chain networks. It is important as well to model the appropriate regulatory and legal considerations, balancing information flow for the seamless operation of a system of systems, with cybersecurity and privacy to protect city dwellers as they move about, and ensuring that renewable energy resources are equitably shared. An interesting model for efficient energy use in buildings takes its inspiration from the frog, which as a cold-blooded animal conserves energy by exchanging heat with its environment rather than producing it internally. Basking in the sunshine on a cool day, plunging into water on a hot one, and becoming dormant in winter when resources are scarce. That is why at Rensselaer, we are modeling climate-adaptive cyber-physical building systems that also behave differently in different weather and seasons. Such systems work with the ambient climatic conditions rather than fighting them. They dynamically optimize the thermal behavior of a building for comfort and energy efficiency. On a hot day, a vascular system sends circulating fluid into the ground for shallow geothermal cooling, or to the windy side of the structure for wind cooling. On a cold day, it sends the fluid deep into the ground for geothermal heating and to the roof for solar heating. This climate-adaptive model could have broad applicability as a design and construction framework for structures of all kinds and purposes. Such structures would be sentient, aware of their environment, in the moment, as they control the vascular system, using artificial intelligence, data analytics, and high-performance computing to make predictions based on weather reports and typical occupancy, preparing ahead of time to keep people comfortable and supplied with the energy required in all conditions. Such buildings also would be autonomous, generating and storing their own renewable energy by taking advantage of ambient conditions, such as the wind channeling that occurs in urban environments. However, at the level of the city, the renewable energy they rely upon should be a shared resource with urban-scale infrastructure that allows for energy exchanges between different parts of the city. We also envision a new model of urban planning that we have named infomorphism, in which cities are evaluated and designed based on their local renewable energy potential, whether solar, geothermal, wind, or water. At our university, we are developing algorithms to identify the most fertile ground for development and to predict possible futures in terms of these indigenous energy resources. Looking ahead, we also need to advance individual technologies for the sustainable cities of the future. As we electrify transport to eliminate emissions, we should look to the skies as well as the roads. For example, at Rensselaer, we are designing emissions-free electric vertical takeoff and landing aircraft that can alleviate congestion on crowded city streets. Unlike traditional helicopters, which use a mechanical drivetrain for a single rotor, these will be multi-rotor craft of many different potential configurations. These electric aircraft are expected to be safer, less expensive to operate, and quieter than conventional helicopters. Unlike today's drones, they will be large enough to carry multiple passengers or to ferry a large volume of goods. Of course, fully electrifying transport requires long overdue advances in energy storage to address the limitations of lithium-ion batteries. Therefore, we are creating self-healing batteries that do not short out, and solid electrolytes to replace flammable organic liquid electrolytes. We also are looking well beyond lithium-ion batteries to less expensive, safer, more energy-dense batteries with novel electrode designs and made of earth-abundant materials, including magnesium, sodium, potassium, or calcium. Energy, however, is not the only resource that must be conserved. Forging better urban-rural connections is important to ensuring sufficient supplies of food and water. In many places, food crops, livestock, and fisheries already are threatened by climate change. Agriculture itself contributes substantially to climate change. About a quarter of global greenhouse gas emissions are due to agriculture, forestry, and other land use. Controlled environment agriculture in vertical farms and greenhouses may be part of the answer. LED-based smart control systems offer a new level of sophistication in vertical farming. As a digital technology, LED lighting can be precisely controlled in terms of color and intensity to optimize the growth rates of specific crops, even their nutritional content. It can even collect optical signals from the plant, data that can help farmers to make adjustments based on the progress of the crop, improving outcomes, and saving water, energy, and other resources. Because the vertical farms enabled by these smart control systems can be sited anywhere, including in urban areas, they can help to reduce the energy costs of transporting farm products. Cities of the future must have adequate freshwater resources. According to the United Nations, 2.3 billion people already live in water-stressed countries, a problem that climate change is exacerbating. Here in the United States, even in geographies with abundant water, we have had crises of water contamination. To protect our freshwater resources, we first need to understand them. Again, universities, in partnership with other sectors, including civil society, are critical. This is why Rensselaer joined forces with IBM and the environmental nonprofit, the Fund for Lake George, to create the Jefferson Project, which takes a system of systems view of bodies of fresh water. We make lakes smart by putting in and around them intelligent sensor platforms that generate enormous amounts of streaming data about weather, water runoff, water circulation, and water quality. The data generate important insights through the use of sophisticated analytics, high-performance computing, modeling, and data visualization. These data also are combined with other monitoring and experimental data to create a thorough and predictive understanding of the factors that drive the food web and overall water quality. An interesting example is Skaneateles Lake in New York State, which serves as a drinking water supply for over 200,000 people. That water supply is threatened by toxic algae, a problem shared by bodies of water around the world. In Skaneateles Lake, our advanced monitoring systems identified a way to control the algae in the short term by understanding how effluent discharges interact with a unique SAISH wave in the lake. In the long term, a universal solution will require understanding the interaction of wave motion, human-generated wastes, and the biochemistry and genetics of cyanotoxins produced by the algae. In envisioning the cities of the future, our current COVID-19 pandemic challenges us to envision and design high-density environments that promote human health and prevent the spread of infectious diseases. To be truly successful, new and expanding cities must make their benefits available to all their citizens. Billions of new urban dwellers in the next 30 years present a daunting challenge, yet one of the most exciting opportunities imaginable. As we decarbonize urban life and make it more resilient, we support the human flourishing that cities always have aspired to. Thank you.